Hello, Shahab Ahmed welcomes you on the channel Defying Mediocrity. And today's discussion will be about alkynes, its preparations and its reactions. We'll prepare alkynes from Vicinal Dihalides in the presence of alcoholic KOH. Then we'll prepare it from Tetrahaloalkanes when two adjacent carbon atoms contain four halogen atoms. We'll discuss that. And then we will discuss the reactions of alkynes. First of all, the reactions of terminal alkynes because of this acidic proton. We will discuss its reaction with a strong base like sodium amide. Then we will discuss its reaction with the reagents like Tollens reagents or Thalling reagents. Then we will discuss its reaction with sodium, like metallic sodium, how it reacts with sodium. Terminal and non-terminal alkynes, what is the difference of the reactivity toward metallic sodium. Then we will discuss its reaction with the water, that is hydration of alkynes. Then we will discuss hydrohalogenations of alkynes. Then under scientific inquiry will come the halogenations of alkynes. Then after that we'll carry on and discuss ozonolysis of oxidation to carboxylic acid. And then at the end, we'll discuss hydrogenations of alkynes. So this will be for today's discussion. So hope you're ready for it. So here we are with our first reaction. That is the preparation of alkynes from Vicinal Dihalides. And here in this case, I am taking as an example vicinal dibromide. What is vicinal molecule? A molecule containing two halogen atoms here, vicinal dihalide I mean, two halogen atoms, 8 consecutive carbon atoms. So both of these halogens, we will abstract them one by one in each step. So this is a two-step mechanism. In one step, one halogen will leave with the hydrogen at the consecutive carbon atom, and in the next step another halogen will leave with another proton from the next carbon atom. Okay, so what happens at step 1? At step 1 we see the elimination of this proton with this bromine atom. Okay, so how does this happen? This happens in the presence of alcoholic KOH. What does alcoholic KOH do to our reaction, our reactants? What does it do? It does elimination. How it does it is the OH from KOH reacts with the alcohol from the medium. It forms a strong base, like here in this case ethoxide ion in water formation. So this ethoxide ion abstract proton from over here. So as this proton is leaving, it leaves its electron on this carbon atom. So here the increase in electron density makes the electron shift toward this carbon in formation of a double bond. Okay, as a double bond is in making, so this carbon pushes this bromine out of the bond. Okay, out of the belonging. So here we see E2 mechanism, the formation of a double bond and elimination of entities. So this proton leaves with this ion, and here this bromine is pushed out as Br minus. Okay, and we see the formation of a double bond. Okay, so we have now converted our vicinal dibromide into bromoalkene. Now what happens in the next step? This we will discuss the next step. This bromide ion combines with the potash to form KBr as mentioned over there. So Next, in the next step, we could have taken KOH again in alcohol, but this bromine is not gonna leave so easily because it is in coordination with this double bond. So there is a partial double bond character in this bond. This is not a simple single bond between a carbon atom and a halogen atom. So what does happen? We need a stronger base, like here in this case sodium amide. The sodium amide is much stronger base than sodium hydroxide. So what happens is that this sodium amide, this amide molecule, sorry, this amide ion abstract proton from over here. Okay, this one or this one, anyway. And the same thing happens. This bromine now is gonna leave. So this leaves as a bromide and combines with the sodium to form sodium bromide. And we see the formation of an alkyne. So this was all about it. Second prep is the preparation of alkynes from a molecule like 1,1,2,2 tetrabromoethane, a molecule that contains 4 bromine atoms, halogen atoms, and consecutive carbon atoms, 2 at one and 2 at the other. When we take this in alcoholic medium and sprinkle some zinc dust to it, we will see the conversion of this molecule into alkyne. Okay, what happens is that this zinc, which could easily be oxidized into Zn plus 2 electrons, these electrons are eaten up by this molecule. So these electrons are donated to the bromine atoms attached at the carbon atoms and make them leave. Okay, so these bromine atoms leave their sites, and as a result we see the formation of double bond. And then when the other 2 bromine leave, we see the formation of another bond, another pi bond, and as a result we see the conversion of this single bond into a triple bond. And what is the role of alcohol? So there are 2 functions. One, this zinc could not be oxidized by the year, etc. Second, the Zn Br2 formation, it solvates this, and we will discuss the reactions of alkynes. And the first one in them is the reaction due to its acidic nature. So if I have a triple bond at the end of the chain, like in this case, what happens is I get a proton attached to the triple bonded carbon with another carbon. So these protons become acidic. Why? Because it is attached to the carbon through sp hybrid orbital. Okay, here the carbon is using its sp hybrid orbital, and that sp hybrid orbital contains 50% of s character, and that makes them more acidic, more electronegative than its other counterparts. Like in alkenes, you will get its pKa value of 44. In alkynes, you get 25. So there is a hell of a difference. There is quite a big difference between 25 and 44 of pKa value. So here you see more S character, 50% S character, while in alkenes we see 33% of S character, while in alkanes 25%. So the S character decreases, so does its acidity decreases, the acidity of this hydrogen. So this hydrogen is attached to this carbon through sp hybrid orbital, which contains greater S character and which is more electronegative. So this becomes electronegative. This carbon becomes electronegative and the proton electropositive. So there could be a rift. This carbon could be broken. This bond could be broken, and this proton could be taken up by a strong base. Like here in this case, we use sodium amide, and it takes up this proton from a bit of acidic compound like terminal alkyne. What the sodium attaches over here, for what the sodium attaches over here, it as this become an ion. So the sodium comes and attaches over here to this ion, okay, and we get a proton attached to NH2 minus. Okay, so the NH2 minus takes up this proton and converts into ammonia, and the sodium is gets attached over here, and we get an ionic compound like sodium alkanide. Here we call it. If it was acetylene, we would call it sodium acetylide. So this is the reaction because of what? Because of this acidic proton. So this acidic proton is here taken up by the amide NH2 minus. NH2 minus takes up this proton and convert this molecule to what? Sodium acetylide, uh, sodium alkanide, sodium acetylide, etc. So this was all about it. Now we will go further and discuss few more reactions about its acidity. Here is another reaction because of the acidity of proton that is present at the end of the chain. So you will see these reaction given by just the terminal alkynes. Terminal alkynes are those alkynes that contains the triple bond at the end of the chain. So you will see the terminal alkynes containing that acidic proton, and that acidic proton could be replaced by these metals, like here in silver and copper. Silver and copper could replace these acidic protons. So I have taken as an example an acetylene. Acetylene protons are replaced by here the metal like silver ion. Silver ion replaces the protons of the acetylene. Okay, these acidic protons. If we take ammoniacal solution of silver and copper salts, we get their respective acetylides. Like here I'm getting disilver acetylide, and here I'm getting dicopper acetylide. One is white PPT, the other is red PPT. What to be remembered is these are explosive in dry conditions, so these must be converted into other products like acetylene again with the help of an acid like HNO3, etc. So what I'm trying to say is we have converted an acetylene into a precipitate. This could be a test for the presence of the terminal alkyne. If a triple bond is present at the terminal end or not. If it is present, you will see a PPT formation. Here in this case, a white PPT formation. Here in this case, you will see a red PPT formation, as you will see the precipitate of a dicopper acetylide. So this was all about this reaction. Again, I must say this, that these reactions are given just by the terminal alkynes. So the acidic proton are replaced by uh, the ions of the metals. This was all about it. Okay, here again, we will see the difference in the reaction of terminal and non-terminal alkynes. If I have a terminal alkynes, like here I'm taking the example of acetylene. When I put acetylene in a liquid ammonia medium and put some sodium in that medium, I will see the conversion of that acetylene into acetylide. Okay, if I were to have a non-terminal alkyne and react it in the same medium with the same reagent, I'll see a different product like transalkene in this case. Okay, so the non-terminal alkynes does not give the same reaction as the terminal alkyne. So this must be remembered. Here, the difference in reactivity could be seen visibly. Okay, this. So here now we will discuss the hydration of the triple bond alkynes. As we discussed the hydration of alkenes in detail, we discussed the Markovnikov's rule, the stability of carbocation, 3 degree, 2 degree, etc. And we did not see the hydration of alkenes any catalyst like like in this case we are seeing the Ag, the mercury kind. What is the use of mercury kind? This could be the discussion for another lecture, but here we will discuss this simply that according to Markovnikov's rule, the positive side of our reagent will add up as Markovnikov says that if the reagent is unsymmetric, which we are adding to a double bond or triple bond, we will see the addition of the positive side toward the side of the double or triple bond that contains greater number of hydrogen atoms. So here in this case, our double and our triple bond is unsymmetric and our reagent is unsymmetric. So the positive side of our reagent will add up to the side of the double bond that contains greater number of hydrogen atoms. So we will see the hydrogen adding up to this side. Okay, to the other side, we will see the addition of OH. So we see our product like this. This is according to Markovnikov's rule. Why does this happen? We have discussed this in detail in alkenes. Okay, now here we will see this is called enol because the OH is attached to carbon which is double bonded to another carbon, not singly bonded, not normal alcohol. This is enol. So this enol tautomerize. So we will see tautomerism. We see tautomerism over here. Okay. What happens is the shift of this proton to this carbon atom. This is called tautomerism. We see X is doubly bonded. We see X singly bonded to Y, which is doubly bonded to Z. So what happens is we will see a proton with X. So what happens is the proton shifts to Z and the double bond shifts between X and Y. So we see. So the situation like this has arisen over here. Between Y and Z, this is a double bond. And between X and Y, we see a single bond, but X contains a proton. So this proton could be shifted toward our Z, that is the carbon over here. So we see the proton shift toward this carbon. So the hydrogen, we will see 3 hydrogen over here. So 1 hydrogen adds up and we see 3 hydrogens and the double bond shifts toward oxygen as we see in this case. So this double bond is shifted toward this oxygen atom and we see carbon double bonded to oxygen and we see free hydrogen with this carbon. So we see CH3 over here. This is called ketone. Okay, so we see a tautomerism between keto form and enol form, but we will see greater stability for the keto form. Why? Because carbon oxygen double bond is more stable than carbon carbon double bond. Okay, so normally you will see the keto form more stable, more in the reaction chamber than our enol form. So hope this was clear. We are here to discuss the ozonolysis of our triple bond alkynes. So what does ozone do is it breaks the chain of the carbons at the side of the triple bond. As we discussed in the alkenes part, that it breaks the chain of the carbon at the site of the double bond. Over there, we saw the breaking of the bond at the site of the double bond, and we saw the formation of C double bond O and C double bond O. Again, over here, we will see the same case. The oxygen will add up to both the side, but with that, we'll see the addition of hydroxyl 2. So in the case of alkenes, we got aldehydes and ketones, but over here, we will get carboxylic acids. And again, alkynes when add ozone, it converts into ozonide, as in the case of alkenes. Now we saw mole ozonide and then ozonide. So detailed mechanism was discussed in alkenes, but here we will go were not worth the details. So the alkynes convert into ozonide. Ozonide, then when we add water to the ozonide, it converts into a compound that contains carbonyl compounds at consecutive carbon atoms. So here two oxo groups at the consecutive carbon atoms. What happens next when I oxidize this compound? This bond breaks at this side, the side of the triple bond, and I see the addition of OH to both the carbon atoms. Okay, so the di 1,2-dicarbonyl compound converts into carboxylic acids, two molecules of carboxylic acid. Okay, so I saw the splitting of the carbon chain at the site of the triple bond. Here, first of all, this triple bond got converted into this compound and then again into these two compounds. Okay, because the carbon-carbon bond split at the site of the triple bond, and I saw the formation of carboxylic acid molecules, two different molecules. If I were having two distinct group at the site of the triple bond. So hydrohalogenation, the same Markovnikov you will see in asymmetrical kinds. Here, as we see, this is asymmetrical kind and the reagent is also asymmetric. So what happens is our alkyne is converted. First of all, HBr, H will add up to the side. Now you know the Markovnikovs that H will add up to the side that contains greater number of hydrogen atoms, and Br to the side that contains lesser number. So why this happens, we have discussed this in alkenes, that it is due to stability of carbocation. Okay, so we get the product of bromoalkene. Okay, now in the second step, what happens? We add another HBr molecule. Okay, so another HBr, H will add up to the side that contains greater number of hydrogen atoms, and Br to the side that contains a lesser number of hydrogen atoms. So Br will add up over here. What am I seeing? I am seeing a geminal halide formation. Okay, a geminal halide formation. What I saw is the formation of a compound containing two halogen atoms at the same carbon atom from our alkyne, which was unsymmetric, and I added an unsymmetric reagent like HBr to this. Halogenation. We discussed the detailed mechanism of halogenations in alkenes. Here we will not go to the details. Here we will see two bromine molecules adding up to our alkyne in two steps. First of all, the alkyne adds two bromine, no, the two bromine atoms, one bromine molecule at the respective carbons of the triple bond. One over here, one over here. So we will see a trans. So the last reaction for today's discussion is the hydrogenation of alkynes. So we can add hydrogen to our unsaturated compound, that is our alkyne, and convert it into a saturated alkane. So this happens in the presence of a catalyst like nickel, platinum, or palladium. For nickel, you need higher temperature. For palladium or platinum, you need lower temperature. It can happen at room temperature. Okay, what happens is two hydrogen molecules are added. In the first, the to alkyne, one molecule adds up, it converts into alkene, and then alkene adds up another hydrogen molecule, converts into alkane. You cannot stop, like these catalysts are very effective, so you cannot stop the reaction at alkene. If you want to stop the reaction at alkene, you need a Lindlardt catalyst. What is Lindlardt catalyst? It is made up of barium sulfate that is coated with palladium, and that palladium is then poisoned with quinoline. Okay, so this quinoline poisoning stops the reaction at alkene, and you will see the formation of a cis alkene because both the hydrogens uh, are added by syn addition, and you will see the formation of a cis alkene. So this was all about today's discussion of alkynes. Trans-bromoalkene were here. Then again, this unsaturation adds up another bromine molecule. Okay, one bromine at one carbon and another bromine at the other carbon, and we see tetrabromoalkane is our product. So this was two-step mechanism, two-step reaction. In one step we got dibromoalkene, still unsaturated, and then again to that unsaturation addition of another bromine molecule and tetrabromo saturation at the end. This happens in non-polar medium. We discussed this, what happens if it happens in polar medium like water. So for that you must watch our video on alkenes.